All right, welcome everybody to our next double installment, first talk of that. This time around, Jaquelin Noronha-Hostler is giving us an introduction to, well, neutron stars, and in the second one, in the second talk, work she's done on that. She has gotten her PhD in Frankfurt of all places, and then moved on to quite a number of places all across the planet. I read Sao Paulo, I see Columbia University, I see Houston, before she joined the faculty at Rutgers, and from there went on to Urbana-Champaign, where she is right now. She got a couple of research prizes, and she's active organizing science, being in committees, the Muses collaboration and research collaboration, for example. But apparently she still finds time to actually do science besides this, and we are very happy to have her to give us a glimpse at what she's doing. And so please take it away.
All right, thank you very much. And so the idea that I hope is okay with this lecture is I wanted to kind of go over the basics of neutron stars, both how they form, how we understand their properties, how we observe them, and then next week I'll get into more of kind of the modern constraints and what we actually know from observational and experimental data. And so to get started, let's just go off the bat what neutron stars are. Essentially, they're dead stars. And so what I mean by that is that you had in the past main sequence stars. So that would be something similar to our sun, which is alive, it's still burning. And of course, you can get many, many heavier stars that are main sequence stars beyond our sun. And you could have something that's on the order of magnitude about 10 to 25 times the mass of our sun. And so that's typically the size of a star that would die and become a neutron star in its final state. And so any stars that would be lighter than that, something like our own sun, would be a dwarf. They go into, our sun would probably become a brown dwarf, but other ones that are slightly heavier would be something like a white dwarf. And we'll talk about those a bit more. And then ones that would be heavier than things that become neutron stars would then be something like a black hole. And so if we think about some sort of generic star that's burning off its fuel, and then it runs out of fuel eventually, and it goes underneath some sort of collapse, goes underneath a supernova, there's three sort of end states that we're interested in this specific talk. That's black holes. So I'll just use the shorthand BH. There's white dwarfs, WD, and then there's neutron stars, which are NS. And so we have neutron stars and white dwarfs. And so it kind of goes from heaviest to lightest. And so essentially what happens is that they burn all of their fuel, and they undergo some sort of collapse, which would be known as a supernova. You get some sort of spectacular explosion that sheds a lot of their layers. And so the idea is that you don't have the same mass that you initially had of like 10 to 25 solar masses. In fact, the final state neutron star mass is much smaller. So this is the neutron star mass is on the order of something like 1 to 2 times the mass of the sun. So you see you've burned off quite a bit, you've ejected quite a lot, and it's much more compact than it was before as well. Good. So that's kind of the general idea of how you would form a neutron star. There's a lot more physics that goes into it that I won't get into this specific talk. Instead, what I want to focus on is what happens as you go from something, let's see, as you go from, oh, that's not the, sorry. There used to be a little thing where I could project. Yes, there we go. As you go from a white dwarf into a neutron star, and also what's the limit between neutron stars and black holes. And that's going to be what I'm focusing on much more in this talk. So let's talk about white dwarfs a little bit. is essentially you have to have something that stabilizes the star so it doesn't further collapse. So if you have some sort of star like this, some generic object, you have on one hand the force of gravity that's pulling you inwards. And so you need something to counterbalance that force for the star to be stable. If you have a white dwarf, you have some sort of electron degeneracy pressure. And so what you can think of this as, if you have your electron states, they have spin, they fill up different levels. And so essentially from that, filling of levels, that's what is stabilizing the star against the whole pressure of gravity. We call it electron degeneracy. And this is what stabilizes the star. And so just because of these two forces, one going inwards and one outwards, you can actually define the properties of the star. And we'll get to that in a second. Now, for a neutron star, it's different. If you have a neutron star, then, of course, you still have the force of gravity pulling you inwards. But the thing that's actually pushing you outwards is a bit more complex. Is you could have neutrons that are pushing you outwards, or you could even have something like hyperons, or you could have something like quarks. And so that sort of depends on what's the interior of the neutron star. In fact, you can get different layers, ones that would have more like neutrons or protons, another one that would have strange particles, another one that have quarks, which we'll get into that later on. But generally, the easiest thing is to think about is some sort of neutron degeneracy. But you could have, of course, or hyperons or quarks. And then if you have something like a black hole, there isn't something else pushing it outwards. This was something that was an unstable star, it completely collapsed. It's a singularity. So you can think of this as unstable. We don't have that other pressure pushing us outwards. And that's why this is really something that happens from really, really massive stars. You just have too much mass that even the neutron degeneracy cannot push you outwards enough to stabilize the star. All right, so how do we actually know the properties of the star? Right, and so the things that we'd like to know what's the mass of a star, we'd like to know its radius. And the other thing that we'd like to know is essentially how squishy is the star. And so that, this sort of squishiness of the star is defined by something called the tidal deformability. And we'll get to later on how we actually define that thing. But what we can do is, for the time being, we can ignore stuff like GR. We can think of something that's complete Newtonian gravity and try and understand the property of the star from a kind of more simplistic picture. And so if you have a star here, we can imagine that this star is an ideal fluid and that it's spherically symmetric. And so in this case, you can take a very, very tiny fluid cell like this. And on one side of that fluid cell, of course, you have the force of gravity pushing you inwards. And on the other side, you have your electron degeneracy pressure pushing you outwards. And you have some very tiny dr, which is, just the change in radius for that little fluid cell. And then we go back to our physics 101. Remember that pressure is equal to force over area. And we have PR plus dr equals FR plus dr over A. This is basically the force on top of the fluid cell. And then you could also have the force coming from the bottom, which would be P of R equals F of R divided by A. So the force then is just the force of gravity. And so for the force of gravity, when you have a tiny fluid cell like this, it's just minus G, the gravitational constant, M delta M over R squared. And then we can also figure out what the mass is because we're assuming this is a sphere, right? And so if you have a sphere, you know the density, you can just integrate outwards. And so the mass of R is equal to 0 to R 4 pi R squared rho of R dr. And we could also write this in the differential form if we had a very tiny piece of mass of dm equals 4 pi R squared rho of R dr, or you could also write it more simply or more compactly, rho dr dA. We have a tiny piece of the area. And so the kind of underlying assumption when you have here is that you're conserving mass and that it's spherical. Now we will eventually peel back that assumption as we go further and discuss more of the properties of the star. But for now, assuming that it's a sphere is a good assumption. All right, so now we have actually one equation that's very important that we'll need to solve later on. This is the one for mass conservation. We still need a second equation. And so to get at that, we can take, here we go. We can take the force from the pressure, which we can take P of R dA minus P R plus dr dA. This can then just be rewritten as P of R plus dP, this dot dr, this little part. And if we work out the math here, we end up with minus dP dr dr dA. So if you have something that's in equilibrium, it's called hydrostatic equilibrium. Then our forces here have to be completely, perfectly counterbalanced. So that means that this force has to be exactly equal to this force, otherwise our star is unstable and it would collapse. And so we can put in that assumption, essentially Fg plus F from the pressure has to be equal to 0. In other words, you don't have any acceleration. And so that just means you get to pick up a minus sign and you set the two equal to each other. And so then you can plug everything in and you get minus Gm delta M over R squared equals dP dr dr dA. We can also substitute in this infinitesimal piece of mass, dr dA here. And we end up with minus GMR rho, dr dA over R squared equals dP dr dr dA. We can cancel a few things out. And we end up with our final equation, which is dP dr equals minus GM R squared rho. So now essentially we have two equations. We have a way to define how the pressure changes with the radius. And inside this equation here, we have our density. This is our mass density. And then if we go up here, we have a way to solve for the mass of R. Now, one thing though, generally, we don't really want to have the relationship between the pressure and the mass density. That's not necessarily something most intuitive for us, especially as we're thinking about a neutron star. It's a bit more complicated. You want relativistic systems. And so what it would be easier to do is instead define an energy density. And so for that, we just take E equals rho c squared, and we can plug that into our two equations. And so when we do that, we end up with what is called the structure equations. And so that is dP dr equals minus g m of r epsilon of r squared over c squared. And we have m of r equals 0 to r 4 pi r squared dr epsilon of r c squared. All right. And so now we have two equations. But the issue is that we still have more than two unknowns. So we do not know the mass, we do not know the radius, we do not know the pressure, and we do not know the energy density. And so what we need actually is a relationship between these two that'll make our life simpler. And so you have what is called the equation of state. Or I'll often abbreviate as EOS. And that is our relationship between pressure and energy density. Now, what goes into an equation of state typically is this deals with the microscopic properties of whatever is inside of your fluid. So for instance, the pressure, if you think about, you have some sort of gas and it's full of little particles moving around. If you have a large pressure, it's typically because those particles are moving very fast. They're hitting the sides of the canister quite a bit, and it would be very hard to push down on the lid of the canister. Whereas if you have a low pressure, they might not be hitting the sides of the walls of the canister as much, and it would be easier to push it down. And so we call a low pressure something like soft, because it's easier to compress it. Or if it's hard to compress it, we call it hard. So soft equals small p, hard is equal to large p. And you generally mean for a fixed energy density. And of course, energy then, that takes into account the masses of the particles, whatever the degrees of freedom that you're interested in, and it also takes into account the kinetic energy of them as well. And so essentially you have a relationship between kind of what the mass of these particles are, their kinetic energy, and essentially how squishy you can think of the fluid to be, or gas, either way. And so this is your equation of state. And why is the equation of state interesting? Well, this would change depending on what the underlying degrees of freedom are within your star. If you have something like electrons, that'll look very different than if you had neutrons inside your star, or if you had quarks inside your star. And so depending on what the underlying degrees of freedom are, you might get a very different equation of state. And so that's something that we'll be discussing as we go through this talk. All right, so now at the end of the day, we have two coupled differential equations. And we want to do something with them. So how do we actually solve them? So essentially, one, need an equation of state. So P versus epsilon. So you need to know sort of what are the underlying degrees of freedom and how to calculate them thermodynamically. Two, the next thing you need an initial condition for epsilon of C. So epsilon of C is essentially choosing, I have some star, here's my center of the star, and the central at the very, basically radius is equal to 0. All right, here's my radial coordinate. At the point that r is equal to 0, that is my central energy density. And so one thing, just in terms of notation, r is my radial coordinate as I am basically varying from the center of the star out to the edge. If I want to define something as the total radius of the star, that is going to be big R. So just to know my notation. I'll use the same for mass. If I'm talking about the mass at a specific R, I'll use lowercase m. But if I'm talking about the total mass, then I'd write something like M, or I could write M of R, just in terms of notation. So we use the lowercase to talk about the actual coordinate. Good. And now I need a third thing. I know where to start my integration for these couple differential equations, but I also need to know where to end. And so if I go and I start from here, I integrate outwards, what happens at the surface of the star is essentially that we don't have any pressure anymore. We've come to the surface, there's nothing that's pressing anymore. And so at the surface, integrate until P equals 0. And that is the surface of the star. Great. Now, the other things that we should know is that our radius starts from 0 here, and then we'll figure out how it looks like for the rest of the star. Okay. So just to give you an idea of kind of how this process works, is imagine I have some equation of state, relationship between P versus E. And that looks like this, right? Good. And so then what I want to do is I actually want to start, and I'm going to integrate here. This is my central density. And then I'm going to integrate outwards until I hit P is equal to 0. And so that will then give me a relationship between the mass and the radius. Let me switch that over. That looks kind of like this. So let me explain. For a specific energy density, I'm going to get a point over here that might look like this. And that corresponds to that specific energy density. I could take another point here, where this is a different energy density. I'm also integrating down to 0, and that corresponds to a different point in this curve. And so essentially what I'm doing is I'm going to pick many, many different central energy densities along this curve. And from there, I integrate until I get this is called a mass radius curve or mass radius sequence over here. So the idea is that if I know my equation of state for sure, then I know essentially what the mass and radius are of any neutron star in the entire universe. They should lie on this line, essentially. Now, one question that you should be asking yourself is, are there exceptions to this? And there are a few exceptions to this. For instance, if the star is spinning, if the star also had something, kind of more crazy, like you had dark matter in the star or a large magnetic field. So there's some sort of extreme cases that can break this. But generally, most of the neutron stars that we're seeing are not spinning that fast. In fact, if they spin too fast, there's something called the mass shedding limit, where they would just shred apart and no longer be a neutron star. They'll not be stable, essentially. So what that means is most of our neutron stars in the universe should fit right on this line if we knew the precise equation of state. By the way, if you have any questions, feel free to stop me and ask. I'm happy to answer them as we go along. All right. So to give you an idea of what this looks like internally in a star, if I have my pressure versus radius, I could just plot this. And so here's my little coordinate R, and inside the star, it will look something like this. And you integrate out to R. See, it's going to 0 at this point, and you have some sort of maximum at the center of the star. If we look at our mass component here, again, here's our radial component. Here's M of R. Here's our total radius. It would look like this. Sort of flattens out, and that gives you your total radius. And so that's for some specific central density. You've done your integration, and that would be what it looks like internally. All right, now one thing I haven't talked about yet is if I look at this mass radius sequence here, all of a sudden you get this thing that starts curling under. In fact, I could continue drawing this and it would kind of loop around into very, very tiny curls. And so what does this mean exactly? Well, essentially, this point, oops, I need another color. This point here is my maximum mass. Essentially, for that given equation state, I cannot produce a neutron star that's heavier than this. And so that's called the maximum mass. And that actually depends quite a bit on what your equation of state is. Think of it like this. If I had a very soft equation of state, I could compress it quite a bit, and I generally produce lighter stars. Whereas if I have a very heavy or a very stiff equation of state, then I cannot compress it, and the stars end up being more massive, and they generally have a larger radius as well. And so it's closely connected to what your equation of state is. And so for this maximum mass, how do we define this? Essentially, you can take the derivative of dm d central density, and this is 0. So you've increased your central density, and you get a flattening point, this inflection point. And you can actually prove from various methods that if you have something where you have dm d epsilon c, and it's less than 0, it's unstable, will collapse, whereas dm dEc is greater than 0, it's stable. And so what that means here, if we go back here, this central energy density is smaller than this one, and basically you're increasing your essential energy densities and you're going up this line until you reach your maximum mass where dm dEc is 0, and then you've increased your central density and you're actually seeing smaller masses. And so that's the unstable branch. Oops. Okay, good. Now, in this case, up until now, I've used Newtonian gravity. Right, I've used sort of simple structure equations right here. I've just ignored the effect of GR. Now, of course, for a neutron star, you do actually have to care quite a bit about GR, but these equations work very well, at least for white dwarfs. But if you had something like a neutron star, you would need to add other corrections for general relativity, and I can show you what those are in a second. But anyways, before we get into that, let's just talk about white dwarfs for a second. So like I said, is they generally have their degeneracy from electrons. And so they tend to be lighter. Their masses are in the range of up to m less than equal to about 1.4 times the mass of the sun. So they could be the mass of our sun, for instance, a little bit less, a little bit more, around that size. They generally are smaller than our sun, but still quite significantly larger than neutron stars. So neutron stars, the radius of a neutron star is on the order of 10 kilometers, whereas the radius of a white dwarf could be something like 1,000 kilometers or somewhere in this ballpark. So it's quite a bit bigger. They're fluffier than a neutron star. And in fact, you can actually go and derive what the maximum mass of a white dwarf is. This is called max of a white dwarf is the Chandrasekhar limit. And this basically goes into, it depends on like the mass of the hydrogen, the weight of the electron, gravitational constant, and you can sit down and show that. And that ends up being around 1.4 solar masses here. All right, but beyond that point, you really need to have GR. You really need to have something where you can look into to study neutron stars. And so what does that look like? And so for neutron stars, we use the Tolman-Oppenheimer Volkov equation. And if you have seen the movie Oppenheimer, there's actually a point where they're mentioning getting these equations. And so what are the equations? You have dp dr equals negative gm r squared rho 1 plus p over rho c squared 1 plus 4 pi r cubed p m c squared 1 minus 2 gm rc squared minus 1. And the mass actually is the same. M of r equals 0 to r 4 pi r squared rho dr. You, of course, could substitute in to get the energy density. I'm mostly going to be always talking in terms of P versus E, but that's just a simple substitution. And so in the case of solving for neutron stars, solving we call these the TOV equations for shorthand, it's the exact same procedure as before. Is you pick an equation of state. Equation of state, so you have P versus epsilon. You pick a central density, and then you solve till P goes to 0. You get mass versus radius. And so why is this important? Well, for every equation of state, if I pick, let's imagine I pick 3 different equations of state, got something like this, got something like this, and I've got something like this. Then I can go over here and I can define a mass radius curve. And that might look something like this, this, and this, right? And so essentially, for every single equational state over here, I get a very specific mass radius curve here. So why does that matter? Well, first of all, like I said before, if you have something with a large amount of pressure, you generally expect some sort of fluffier star here, and it might reach heavier masses as well. So this is something that we can look for in observational data. In fact, if I could find out the information of the mass and radius of every single neutron star in the universe, I would know exactly what this curve is here. And so in principle, what I can do is I can throw in a bunch of different equations of state and look at observational constraints over here and try and work backwards to get my equation of state on this side. And that's in fact something that people do quite extensively, is you put in various forms of your equation of state and you try and see how it compares to data. You can do a Bayesian analysis by applying, various constraints that exist in the universe. And I'll talk more about what those constraints are next week as well. But anyways, this is a lot of what people are doing, is making this connection. And it's fairly straightforward to actually do this because this is a 1D problem, right? You just have pressure varying with energy density. You don't have, for most neutron stars, you don't have to worry about things like temperature because they've been sitting there. They're very, very old. They're, sometimes, thousands and thousands of years old. And so they've had time to cool, and you can pretty much ignore temperature. You can ignore other properties. And so you end up really just having a 1D problem. Now, there are cases when you don't have that, and you do have to start caring about temperature or other properties of the neutron star. But if you have something where you're just looking at the mass and radius and you're looking at old neutron stars, you can pretty much ignore that. All right, so for that, to do these things, you need constraints. And where do we get those constraints from? We get constraints from X-ray observations. And this is something from NICER specifically. And so what does NICER do is it sits on top of the International Space Station and it just stares out at one specific neutron star. And so it would look at what they call hotspots, something like this, as the neutron star rotates. And so they watch over time how these two hotspots, for instance, are rotating around. And the longer they look at it, the better they can figure out what the radius of that neutron star is. And so that's one way of obtaining information about the mass. Well, mostly the radius. They typically find stars that already know the mass well, and then they're extracting the radius from this. The next thing you can do is get mass measurements. And so why is this relevant? Well, first of all, knowing the maximum mass is super important. This is something that, again, you could see up here. Depending on what your equation state, it could tell you that you have a lighter or heavier neutron star. And so this is something that we're interested in quite a bit. And this is generally from observational data as well. And then the last source that you're getting for the mass and the radius is from LIGO, Virgo, Agra. And that means it's from gravitational waves. Now, this one, I should put like a star here because you're not actually getting, it's not actually the radius. You are definitely getting information about the mass, but what you get from gravitational waves is not directly related to the radius. It's something called the tidal deformability. And I mentioned this briefly at the beginning of the talk, and this is something where it's basically how squishy the star is, right? And so let me explain how it looks like for gravitational waves. Also, one thing I realized, I don't actually know when I should end here. So should I go till the end of the hour or?
You can go as long as you feel you can maintain that story.
Okay. All right.
If it's getting too much for you, wrap it up and be done.
All right, sounds good. So let's talk, to understand tidal deformability, let's talk about the stages of, and I'm going to abbreviate gravitational waves like this, gravitational waves. And so you could have something where you have two compact objects here. I'm not going to really specify. Well, let's just say they're neutron stars. It makes my life easier. And we have mass 1 and mass 2, and they're orbiting around each other. In fact, they're inspiraling. They're getting closer to each other. And they have some distance that's separating them. That's a little r here. Now, if they're really far apart, they essentially look like little points or inspiraling around each other. And so this is called the early inspiral. And so at this point, they don't really feel each other's gravitational pull too much, or at least it's not infecting the shape of these two tiny compact objects. Now, once they start getting closer to each other, they actually feel their gravitational pull. 2 and 1. And you can see that they start to get deformed. And that's from the gravitational pull of each other. And so essentially what happens is, depending on how squishy the star is, so if it has a low pressure, then you can squish it more. If it has a high pressure, it's going to be harder to squish those things. And so they'll stay rounder. And this is actually very closely related to the mass. If I go back to my equation of state up here, you can probably see this a little bit better. If I have a small central energy density, that means that, you know, maybe I'm like here or something like this, then my pressure is lower. As I go out in central energy densities, i.e. having more massive stars, then my pressure is going to increase. In fact, we know for stability reasons that pressure always has to increase with energy density or stay the same. It could be flat, but it's not going to go decrease unless you have something that's unstable. So the point is that we generally expect that for more massive stars, they squish less, and less massive stars, they squish more. It's kind of a good rule of thumb, although there's some ways to break that. And so at this point, you get tidal deformability. This we generally call lambda, and this is called the late in spiral. Now, at some point, these guys actually touch each other, and you get these blobs. This is called the post-merger. This is when temperature matters. Because what ends up happening is it's a collision between two giant stars out in outer space. And so when you collide things, you heat things up, right? Just like if you had a car crash, you would produce a lot of heat. Same thing with neutron stars. And so then temperature definitely matters. And then it does stuff. It flows around each other, does complicate things. And at the end of the day, you can get a remnant. And so you kind of have three options here. You have a black hole. You could get a hypermassive neutron star that at some point might eventually collapse, or you could just get a neutron star that's heavier. If these things were two very light neutron stars, it might produce a heavy neutron star that would be a remnant as well. So I've mentioned all of these things. What can we actually measure today from LIGO? Like, what do we have data on? That actually comes from here. This is measured. This, we know for sure we have something on the latent spiral with tidal deformabilities. That was from GW 170817. Unfortunately, we do not yet really have information about this end here. That's not to say we won't have information. In fact, as LIGO continues to upgrade, we should be able to get information about the post-merger. And as multi-messenger astrophysics improves, we might be able to capture something about the remnant someday as well too. Essentially, that is something that we need to visually see, is we need strong coordination between gravitational wave detectors and observational astronomy, where they can just, you know, go and actually look and know where it is in the sky. They need localization is essentially the key word there to see what's happening afterwards. Now, they have seen a kilonova, and so that is really close. That's already giving a lot of information here, but you'd also want to see essentially what is the final state as well too, what really happens if it's a black hole, hypermassive neutron star, or neutron star. All right. And so the reason that we don't have the ability to measure it is it has an issue with the signal to noise ratio. And like I said, for this, you need multi-messenger astronomy. All right, so let's talk a little bit more about the tidal deformability. I'm not going to derive it for you because it's a very long, complicated thing, but I'll kind of give you a breakdown of how this works. And I will talk to you about what they measure, because that's a little non-trivial. So once the R, the distance separating the two stars between M1 and M2 is small enough, they're then sensitive to the gravitational pull between each other, and they're no longer a sphere. So what do you actually do to get this? Well, there's sort of specific steps. You do a multipolar expansion of the metric exterior of the star. And so this is stuff, if you're familiar with spherical harmonics, right, you can get different types of deformations to something. You can get a quadrupole deformation, you can get an octupole deformation. In fact, this is something that you can go into GR and actually work on deriving. And so you can get all these different moments of the star to understand what it would be deformed like. So hence doing this expansion. So first we get this for the exterior of the star. Then to actually find the tidal deformability, you solve Einstein field equations in the interior of the star to first order in tidal perturbations. And then basically what you do is you match interior and exterior solutions. There's a lot of math that goes under the hood here that I'm not going to get into, but from this procedure, you end up getting a tidal deformability. And so what does that actually look like? The thing that it generally scales with, it scales with the compactness, which is C equals the mass over the radius. So that's how compact the star is. And so I can then write down lambda versus C here, and it will generally look like this. So if I have a more compact star, this means that it's harder to squish it. Smaller tidal, so maybe I can actually just draw for you what that looks like. If I have a small tidal deformability, basically my star is round. And if I have a large tidal deformability, then it's squishier. So it's more deformed. So that's the way to think about this. And then if I translate this over to a mass radius curve, mass radius, here's my curve here. I can imagine here at the maximum mass here, that's when it's the least tidally deformed. It's more or less round. Whereas if I go here and I pick out a light star, then it's very squishy and it's going to be very, very tidally deformed. And so that's a general rule of thumb to think about with tidal deformation. So the issue is ideally if we had, you know, a binary neutron star merger, then if we go back here to this picture, the ideal scenario is we have two stars merging and I get the tidal deformability out for two stars. And then I have two new points on my lambda versus C plot and have a nice constraint for my equation of state. So one thing I should mention is just like with the mass radius curve is for this, you need the equation of state. It definitely depends on the equation of state. And you can use this then to constrain your equation of state in the exact same manner that you could with the mass radius curve. And so that's why there's sort of this little caveat that you have these constraints with tidal deformability, but it's slightly different than the radius. But it provides similar information. Let's say it like that. All right. And so the idea here that in the ideal world, I would measure two neutron stars here and get two different tidal deformabilities. I'd get something like lambda 2 and lambda 1. That'd be great. The issue is that nothing is ever perfect. Life is complicated. And what you actually measure from LIGO is a complicated combination of the two tidal deformabilities. And so you need to break that degeneracy somehow. And so from gravitational waves, let's say today, you don't get lambda 1 and lambda 2. That's supposed to be a 2. Instead, you get this guy here, lambda tilde, which is 16/13 m1 plus 12 m2 m1/4 lambda 1 plus m2 plus 12 m1 m2 to the 4th lambda 2 m1 plus m2 to the 5th. So now what I have, this is what I get out from talking to my friends in LIGO. And I have to somehow figure out the individual lambdas. How do I do this? Well, first of all, let's discuss what M1 and M2 are. They always have this constraint that M1 is less than M2. So M1 is my light star, and M2 is my heavy. And so that means that I can define some ratio, which is M1 over M2, and this always has to be less than 1. So you might see this Q occasionally if you look at LIGO papers. So how do you actually break this degeneracy between M1 and 2? You need to break the degeneracy between M1 and M2. There's two ways you can do this. One, you pick an equation of state, or you pick many equations of state, and you compare to observational data. And then you can break the degeneracy within that framework of those equations of state. The second way to do this is from universal relations. And so the idea here is that there's a way to scale this information in a way that's universal that will then allow me to break those degeneracies between these two neutron stars. And so I'm going to talk quickly about the universal relations here, because this is a cute idea. But there are also interesting ways that these universal relations break that can also tell us about interesting physics as well. So anyways, I want to go through and work through that real quick. So for the universal relations, and I also realize now as I'm going through this, in this talk, I was just going for the pedagogical approach. I haven't really talked about all the references because there's much work. I obviously was not the person who went and solved these things. In my talk next week, I'll have all those references. So there, I guess a bit of an apology that, in fact, one of my co-authors is on this work. So I'll include those references in the talk next week. So you have these two universal relationships between lambda 1 and lambda 2, which is basically doing the symmetric tidal deformability or the asymmetric one. So basically I just, oh, sorry, I forgot a negative sign. This should be negative. So anyways, the symmetric one is you just take the average of the two. The asymmetric one is you take the difference and divide by 2. And so you can then make a plot that looks like this. Lambda A versus lambda S, and you get some sort of line that's more or less like this. Now, if I do many equations of state, they're basically, if we don't have, so assume no phase transitions. If you don't have any phase transitions can break this relationship. But if you don't have phase transitions, you get more or less about a 10% difference between them. So it's not 100% universal, but it's pretty close. And you can take that 10% error and then just, expand this in order to break that degeneracy. So this is one way that they actually break the degeneracy between them, is use this universal relationship. All right, so I'm getting to a little bit more I want to talk about in terms of what actually goes on inside the neutron star, and then I'm almost to the point where I can wrap up. So that's how we observe a neutron star, and this gives to us specific constraints. So in fact, if I were to show you what these constraints that I've talked about for NICER, oh, my stuff's disappearing, you would get something up here. This is around 2 times. This is in terms of the mass of the sun, and this is 1, this is 1.5. And so this is from NICER. I get 2 little blobs here. And in fact, there's now a new one that is right around here. Apologies that it's not necessarily a perfect drawing. I have other plots elsewhere where you can see that. So this is what you'd get the constraints from NICER. From LIGO, you have one constraint that's around 5 plots in terms of mass instead of compactness. It's around 1.4 solar masses. And then I had 2 stars that look like this, essentially for my constraints from tidal deformability. So if you put these constraints together here, you already can eliminate a number of equations of state. First of all, because you get up to 2 solar masses, which is actually hard for many equations of state. And the other thing that constrains it, this constrains it quite a bit, because you can't have for this light star too stiff an equation state or something that's too hard. And so there's many equation state that would be above this constraint that were eliminated because of this. So these things have helped a lot in terms of our understanding of the equation state of neutron stars. But why do we care? What is interesting features within an equation state? Like, what is interesting about it, and what are we looking for? So for an equation of state for neutron stars. So things that we want to know for the pressure versus energy. Could we have quarks in the core of a neutron star? Could we have phase transitions? And then the other issue that we run into is if we actually plot P versus epsilon, it's generally not that interesting looking. So we need other observables that help us identify features within the neutron star more easily. It's more interesting to plot, it's called the speed of sound. So CS squared is dp dE. So we're essentially, you're just taking a derivative of your equation state. And so if I look at some sort of what I might call a boring equation of state, this would be something like neutrons, protons, electrons, then my speed of sound versus my baryon density, or I could do energy density, either way is fine. It's just going to kind of monotonically increase like this. It doesn't look that exciting. But if I had something where I had quarks at the very core of a neutron star, I could get some pretty interesting features. I might get something like a very large bump in my equation state to the point that it might be getting up. This is what's going on here? This is basically the causal limit. So the speed of light is essentially, you get something where the speed of sound starts approaching the speed of light. And there's a specific type of equation state called quarkionic matter that transitions from neutrons and protons into quarks. And it has this very dramatic feature there. Another thing that you might look for in an equation of state is something like this, where you go up and then you have a speed of sound that goes to 0 and then goes back up again. This would be a phase transition, where you'd have quarks here and you could have hadrons here. So we have things like neutrons, protons. You could even have strange particles as well too. But the point here is really this phase transition leads to very dramatic behavior. And so to give you some ideas of what that would look like if you had these equations of state, just qualitatively, what they would do to your mass radius. Oops. If I just have my standard equation of state, it's going to kind of look like here. Neutrons, protons, electrons. If I then have, let's take this quark ionic matter one. If it has a bump in the speed of sound and it happens at an early enough density, it's going to make you kind of bend backwards like this. And you can often get to higher maximum masses. And then if I have something like a phase transition, imagine that looks more or less like this. We could even get something where you get a break in your star, it's unstable, and then you have a second stable branch. And these are called mass twins. And so that's something quite interesting because you could get two stars with the exact same mass in very different radii. And so there's active searches for looking for things like mass twins because that means that you have a phase transition in a neutron star. So this is something people are quite excited about. So to quickly wrap up, I do want to mention why we actually call these things neutron stars, because I haven't really gotten too much to the internal physics of this. So why neutrons? Well, you may have heard about things called beta decays. That is essentially that you have a neutron and it decays into electron, to a proton, and an anti-electron neutrino. This is something that we can measure here on Earth. This is also how nuclei can decay, essentially, is a neutron undergoes beta decay, goes to a proton. This happens quite a bit for nuclei. It's fairly well understood. But what is difficult to do is go in the other direction. But what ends up happening in a neutron star is you've undergone a bunch of beta decays to the point where you have a ton of electrons. You have so many electrons, in fact, that you've filled up all your energy levels. Filled up your electron energy levels. And what that means is that if you've filled up all your electron energy levels, these things go with momentum, where these are like lower momentum, and this is high momentum. And so it could be to the point where you filled up all your energy levels and you can no longer undergo beta decay because you can't produce an electron with a high enough momentum. So what happens in this case? Well, what ends up happening is you undergo inverse beta decays. Inverse beta decays. And so you have electrons plus protons going into neutrons plus an electron neutrino. And so in a neutron star, since you filled up your electron energy levels, you then undergo inverse beta decays, which produces neutrons. Hence, you have a neutron star. It's very, very neutron rich. And so you've undergone a bunch of inverse beta decays and produced a huge amount of neutrons. And just to give you kind of a back of envelope estimate, your neutron star, somehow I'm erasing it, neutron star has at most about 10% protons. It'll be protons and electrons. The rest is neutrons. So essentially 90% of your star is more or less neutrons. Now there are different layers to a neutron star. There's the crust that has a bit different physics, and there's the core that might have interesting physics like quarks in it or hyperons. But if we're talking about the vast majority of a neutron star, it's a very neutron rich object, although those neutrons might be in sort of different phases of matter. They could be stuck within a nucleus. they could be in some sort of nuclear pasta, they could just be interacting with each other. There's sort of different stages that you get within the layers of a neutron star. But generally, the neutron star is 90% neutrons, or even more than that. And so you might have heard a term called beta equilibrium. And so what that means, that you assume that the reaction in this direction is balanced by the reaction in this direction. And so you're in equilibrium, is you have a very specific relationship between your neutrons, protons, and electrons. We don't necessarily include the information about the neutrinos because they, for the most part, unless they're trapped, just sort of fly out of the neutron star. And so ignoring neutrinos, we can write down the chemical potential such that neutron chemical potential is equal to electrons plus the chemical potential of protons. And so if you don't remember, if you're a little rusty on your stat mech, your chemical potential is the amount of energy to add, for instance, this one would be the amount of energy to add another neutron to your system. Or it could be the amount of energy to add another electron to your system, or proton. And so essentially what this is saying is that the amount of energy to add a neutron to the system is equal to the amount of energy to add an electron plus a proton. And that's what it's saying. So that means you're in beta equilibrium. Now, the other nice feature of being in beta equilibrium is that it's electrically neutral. Although the star always has to be electrically neutral. In fact, if you didn't have an electrically neutral star, it would explode. So it doesn't have a net charge to it. So the way that you handle this is basically your number of electrons is equal to your number of protons. And this is, you have this constraint that you add to your star as well. And this occurs even if you have exotic states. You would just have to always make sure that your leptons, so basically more generically, your number of leptons is equal to your net charge of hadrons. And if you think of things like quarks, that's a little bit non-trivial because an up quark carries plus 2/3 charge, a down quark carries minus 2/3 charge. So you have to kind of counterbalance that electric charge between those guys. All right, so that's kind of the overview that I wanted to give you all. I'm done on my end. Do you have any questions for me? Next week, I'm going to talk a lot more about what we actually have inside the star and what we know today.
Let's first say thank you.
Okay.
Then you guys get to ask questions.
Immediately. When you're talking about the equation of state, it depends on the degrees of freedom that we're considering in the star. So if we're talking about if the quark physics is very relevant or if it's just more the neutron physics. So when you're talking about the equation of state, are you talking about a single equation of state that is going to sort of broadly describe most neutron stars, or would you have some big variance between, say, different masses of neutron stars producing equations of state that rely on different degrees of freedom?
Yeah, that's a good question. So let's imagine, let me just draw an equation of state for you here. And essentially, if I have different, if I go up in my energy density, my equation of state has different pieces to it to some extent. And each of those pieces would relate to a different layer of a neutron star. So if I draw a neutron star, I don't know if you all are familiar with jawbreakers, like you hadn't, like I had these as a kid where you kind of like suck on them and they have the different layers of them.
Yeah.
Yeah.
All right.
I don't know, I'm old, so I don't know if other people have those that are still around or not. So what you could imagine is that like this layer here is related to this layer of the neutron star. So the very edge of it, it's mostly, it's nuclei plus electrons, something like this. And so you have this equation of state that relates to here. And now if you keep going inside your star further, you could have something where you have very neutron-rich nuclei, but then it's become so neutron-rich that you can no longer stick another neutron inside of it, and you have free neutrons as well, and you still have your electrons around too. And so this would be your, let me color this in blue. This is your next layer of your neutron star. And so I can keep going here. This is another layer of my neutron star and so forth. And so the idea is that each layer of the neutron star has a different equation of state because of different underlying degrees of freedom. But now if I go to my mass radius curve, that still should have, this is still just one line, right? And so it was still giving me just one mass radius curve from here. So it's the way to think about this is if I have a lighter neutron star here, I might not get through all those layers. I might only get up to this layer here. Whereas if I get to a heavy neutron star, I might get all the way to the heaviest possible layer, which could be quarks. So conceivably, they all come from the same equation of state generically, but it just might be that it's not heavy enough to reach the quark core.
Okay.
Does that make sense?
Yeah, that makes sense.
Mhm.
Okay. I don't know if you can see, there's a question from the
In the
text
chat.
panel.
Yeah.
Okay, I can go there. For neutron stars that have hyperons, what is the percentage of this hyperons inside the star? Oh, that's a great question. It depends a lot in terms of where the hyperons would switch on within the neutron star. I think kind of the earliest that they might start turning on is around 2 times the density of a nucleus. Off the top of my head, I don't know how in terms of how that translates to kilometers of a core of a neutron star. I don't actually know because it would depend a lot if you had hyperons and then still had a quark core, if it was only hyperons inside. But my estimate, if I had to guess, would be like a few kilometers of the core of a neutron star, maybe like 2 or something. But in terms of the overall percentage, it would still be smallish because you're always going to have these outer layers that are very neutron rich. It's only once you get to the very center that you could essentially squeeze nuclear matter enough to get to hyperons.
All right.
More question?
Okay. I have a question relating to your mass radius curve. So you mentioned that it kind of gets to a maximum, starts decreasing, and kind of like some sort of spirals inwards. Is there something special about the point to which it spirals to?
Oh, no. So basically what you do, as you see, I often just draw it to the maximum mass. If I were to keep drawing it, no, we don't really know. We don't even watch it basically after the point that it starts spiraling inwards, with the one exception. So as I said before, you could have very specific types of stars with first order phase transitions that look like this. And so it would be unstable for a bit. It would start going in, but it wouldn't really do it correctly. It would look something like this, and then you get a second stable branch. So if you have something where you could have a second stable branch, there are even cases that you could have a third stable branch. That would be important. But if it really just starts spiraling inwards, no, because then you would need to just describe that as a black hole, basically. And so you would use different methods to, stuff. You could use perturbation theory and GR. You could use numerical relativity, but you'd have to use something else to describe black holes.
Thank you.
More question?
So in the very first slide, you spoke about all these degeneracy pressures, and there's it seems to be a jump from saying, okay, once you reach quarks, beyond that is a black hole. So is that like now definitive proof that there's no substructure there to the quark? Because I can imagine that if there was other stuff, right, then you get another degeneracy pressure pushing out from whatever everything else is made up of. Right?
Or is there an argument that this would have to be this far off that you can't even see it in neutron stars?
Yeah.
Mhm. Yeah, I think that's probably, I mean, so far we have no evidence there's anything beyond a quark or there's any sort of quark substructure. But even if there was, the maximum mass is already sort of iffy if we could reach quarks inside the core of a neutron star. That's something that's hotly debated today, if we can reach large enough densities to actually unlock those degrees of freedom. So even if there was stuff beyond quarks, I suspect that you would need such massively large densities to reach that it would be already sucked into a black hole by that point. Black holes are a bit annoying for us nuclear physicists because, you know, we'd like to keep going to larger and larger densities, and they get in the way for us.
All right, let me ask my obligatory question.
Sure.
I have it. You put these radii in, right, in your suite here. Let's see. One of the typical criteria that you put on, this is theory, I suppose, where you switch from one type of matter to another. And how much uncertainty is in this?
Yeah, that's a great question. And in fact, that is a really important question in terms of, like, once we go from one equation of state here to the next. So on the very low side, it's pretty straightforward. The nice thing is, and I didn't really mention this before, is the low part, the low density part of a neutron star is the same as the entire equation of state from the white dwarf. So we can test this, the low density part, both from white dwarf's information and from neutron star information. So I should make that clear. Now, typically what happens at the low density part is the equation of state, you just kind of add corrections, and it's where those corrections are relevant. So to give you an idea of this, if I go to very, very low densities, essentially my picture is the following: is I have a nucleus. So my nuclei, let's just call them big N here, and I have my electrons. And so my nuclei are a very small part, and I have a bunch of free flowing electrons here. So if I'm at the very outer layer, I just can assume that it's degeneracy pressure from electrons. As I continue to squeeze the matter, eventually I'll have to actually think about, like, the mass of these nuclei playing a role. And if I get closer and closer to the interior, these nuclei, they start to get squeezed. They might even form some sort of lattice that I can take into account. And I can even think of stuff like electrostatic corrections, because I have a huge positive charge from my nucleus and I get a negative charge from the electrons. And so I can take into some sort of account these electrostatic corrections. But really what I can do is I can just have one equation of state that includes all those corrections. It's just that those corrections are very, very tiny here. They're negligible here, but then here they matter. So in some sense, the low density part's a bit easier, is that I can just do that. I also know fairly well from theoretical models where this neutron drip line is. And so this is something that comes out of my model, and I can just calculate one equation of state. In fact, the kind of equation of state that's even used a lot of times today is called BPS, which is from Gordon Bain, who's local to us here in Illinois, and I still get to see around sometimes in the hallways when he's not off traveling to Japan or Europe or something. But anyway, so he was one of the creators of this low density one. And so that one is essentially one giant equation. It covers a lot of territory, but it's just when the corrections show up or not. So it's not like we're worrying about matching. But you're right, you're absolutely right. Like, once we get to the interior of the star, in fact, we want to test a bunch of different equations of state, because there's different possibilities. We might just have neutrons, protons, we might have hyperons, we might have quarks. And then it's really a question of, like, when would I match between equations of state? The good news is that thermodynamics can help us out here. And so if I do something like pressure versus energy density, and I have two equations of state here, generally what I do is I can find a matching point where they meet. And so that's a good way of doing this. Now, you, of course, want the matching point to make sense. So you want something like if you had a hyperon equation of state, you wouldn't want that to start appearing below nuclear saturation density, because that would be strange. We know that the density of all nuclei, that's extremely well known. And so you would want the hyperons to appear at higher densities than that. So there's some playing around with it, but this is kind of generally what you do is you find the matching point between the two. There are some little tricks that you need to do to match them correctly, so it's thermodynamically consistent. But yeah, that's essentially the procedure, what you do. You also, have to figure out what the right phase of matter is. And so there is some techniques that you do for that as well too.
All right. Well,
I have, well, it might be a very astronomy question as opposed to, it's about when doing the actual gravitational wave astronomy on the neutron star mergers. I noticed that when the actual parameter that you get out, the tidal deformation of them both, that lambda tilde, it depends on pretty high powers of their masses. Very high powers of their masses. Is there a problem in the uncertainty that comes out on that parameter? I don't know exactly how precisely measured those masses are relative to the actual uncertainty that you then get out on lambda tilde, for example.
Yeah, that's a great question. So the masses, thankfully, see if I can go to my plot here. The masses from gravitational waves that we know a lot better than almost anything else. So it's not 100% precise, but you always are going to have some error on the masses, but you have a pretty decent idea of the masses. In fact, that's kind of the easier thing to measure. And so if you look at like this plot here, which I drew, I personally put any numbers on this because I don't remember them off the top of my head. But what you can see here is that you kind of get these blobs. These are posteriors from a Bayesian analysis that you have to take into account many different things in terms of like where it is in space and various other parameters that go into like analyzing it from the gravitational wave data. But anyways, you would also definitely have uncertainty on the mass, which is why you got this kind of width to it as well. So yeah, they definitely take that into account, but thankfully they know the mass a lot better than they actually know the tidal deformability. In fact, there has been a number of measurements of binary neutron stars or neutron stars with a black hole where they know the masses of the objects, but getting the actual tidal deformability is very hard. They could put like an upper bound on it, but the problem is it's still consistent with zero. They just don't have the sensitivity. Or the other issue is sometimes they have something interesting happen and not all the detectors are on. And when you have more of the gravitational wave detectors on, you get better information. And so you might have heard recently, like a week or two ago, they announced this big announcement that they found something in the mass gap. And it turns out they did not have all the detectors on, they only had one on. And so they had very little information about it. But they couldn't measure the masses, but the tidal deformability, they couldn't really get at very well.
Okay. All right. Thank you.
You're welcome.
any other questions? Everybody's exhausted. All right. Well, I'm sure you are exhausted now.
Yeah, I need to go get coffee now.
All right. Thank you very much for getting up this early and investing your time in setting us up for a talk next week that I'm very much looking forward to.
Yeah.
Thank you.
Thanks.
Thank you.
Thank you. You're welcome. Have a good day.
You too.
Bye.
All right.